geocentrists and flat earthers often point to as evidence that the Earth does not move, that it's a stationary, immovable object. And so it made me want to really understand what was going on there. And the process of doing that has led me into so many rabbit holes I can't even tell you, but it has been tremendously exciting to me as a physicist to learn things that I never knew before, and that I think most of my fellow physicists probably don't really know very well either. So that's the route we're on, and we are on the penultimate episode today. We're going to finish up next time with Michelson-Morley experiment, which probably everybody's heard of, and of course how it led to the special theory of relativity, and how ultimately then we're going to take a little recap on what the view of all of the things that we've been talking about is from the theory of relativity. So let's see. I guess I should ask Shamash: are you prepared? Shamash does this amazing thing. He takes these episodes and puts them on YouTube in the Scientific Discourse channel on YouTube, which he will put a link to, I think, at some point here. Where are you in the prep for getting that started today, Shamash? You're already live. Oh, excellent.
I thought you were making your introduction, so I pressed it as soon as I can.
Excellent. I was just thinking as I was finishing that introduction that I wished it had been on the live stream. So I'm glad it is.
Three quarters of it is.
Okay, very good. Thank you. Yeah. So anyway, that's another thing. And Shamash will put a link, I think, to the YouTube channel if you want there as well.
Right here, sir. This is the link of our live poster.
All right. Thank you very much. And thank you so much for doing that, Shamash. It's really, this is a remarkable amount of work that Shamash puts into both doing this, also putting Sam Tomasevi's chemistry talks on Monday online, and his own Philosophy Wednesday talks online as well, which is just, we just have a real 1, 2, 3 punch now, I think, with Sam on Mondays, although he's often not able to do that. He's a working stiff. And then Shamash's Philosophy Wednesdays, which really are wonderful. Nice focus on logic and science in philosophy, and kind of the philosophy of mathematics, logic, science, etc. I find them really interesting, and so you should check them out as well. Same time as this on Wednesdays.
What a wonderful plug right there. Thank you so much. I'm glad.
Yeah. Okay, well, let's get right into it. As always, if you'd like to join us on stage, feel free to raise your hand. Actually, I should say hi to Hermes. Hermes, did you want to say anything, or are you just hanging with the cool kids?
I'm hanging with the cool kids.
Okay, we'll bring Les up here on stage. And anybody else who wants to, just raise your hand. We'll have you up here, and then you can interrupt me when I say something stupid and point it out. Hi, Les, are you just hanging with the cool kids for now?
Yeah. I'm just a listener.
All right, very good. Happy to have you here. And so anyway, Shamash will pay attention to who's downstairs and bring you up. Hopefully, if you raise your hand, I'll try to do that as well. And we'll try to keep an eye on the chat as we go. So if you'll open the slides, number 4, this is the 4th in a 5-part series that's motivated by stellar aberration. That's kind of the central organizing theme. Has to do with Aries failure I mentioned before as well, which we will talk about today. But ultimately, this is, as I said, the history of the 18th and 19th century, ideas about light in particular, really just light in particular. So let's start with a recap of parts 1 through 3. Historically, we started by kind of pointing out that around 500 BC, ancient flat earth ideas bit the dust, trivially so, because all ancient cosmologies were based on the idea that there was a celestial sphere and everything was in it. The sun rose every morning in the east, went overhead, obviously went underneath us at night, creating night, set in the west, obviously went underneath us because it came up again in the east. Some cosmologies had tunnels through which the sun traveled, but in some way or another, the sun just went away, and that's what made night. But, something like 2,500, 3,000 years ago, the human race learned that it was night, that it was day in some places when it was still night here. And they weren't morons. They understood that you couldn't do that with the flat earth. So the flat earth was gone once and for all. We all thought until about 10 years ago. But that's another story we won't get into. At that point, the only question was, what was the place of the globe Earth in the universe? And that's a question that's much harder to answer. And for some 2,000 years, it was presumed, for obvious reasons, that the Earth was the center of the universe. As I've mentioned several times, that was only obvious because of gravity. Gravity could be nothing more than the desire of stuff to get to the center of the universe. That's why things fell when you let them go. They would try to get to the center of the universe, and they'd get as close as they could. All of that was perfectly obvious until, at some point, Copernicus kind of had the idea that you could explain the motions of the planets and the sun and the moon, etc., if you put the sun at the center of the universe and interpreted the Earth as just one of the planets. But that was a huge pill to swallow, unlike the flat Earth, which, as I said, as soon as we knew there was night and day at the same time at different places, there was no way the Earth could be flat. So that was gone. But it was a much larger pill to swallow to imagine that the Earth wasn't at the center of the universe because among other things, you had to explain gravity, etc. So all of that was a little bit of a problem, but the increasing attractiveness of a heliocentric model in terms of the simplicity that it renders for observed motions in the sky, made it more and more attractive until finally in 1687, when Newton published his Principia with his laws of gravity and laws of motion, and explained not only why we had a heliocentric universe, but exactly how it worked, exactly the surprisingly simple laws that governed all mechanical motions in the heavens and on Earth. That was such a powerful success that lingering geocentric ideas at that point bit the dust. That was no longer an option in the wake of Newton. So we have now, at the end of the 17th century, a clearly established heliocentric model. And then the question comes, well, okay, so what can you do with that? And one of the first things that was discovered was understood was that this ought to give us a way to determine how far it is to the nearest stars. Assuming the stars are things, we will see parallax. As the Earth revolves around the sun, we'll see parallax. We'll see the nearest stars kind of wagging back and forth, just like near things in your field of view do when you wag your head back and forth. And that's what Bradley was doing in 1729 when he created a telescope that was sensitive to motions of the stars from their average positions by something like 4 or 5 seconds of arc. He could maybe even as low as 1 second of arc. He could actually detect the motions of stars back and forth around their mean positions. And so he was looking for stellar aberration when he saw something that looked a lot like stellar aberration. He was looking for stellar parallax when he saw something that looked a lot like stellar parallax, except it was 90 degrees out of phase. Rather than wagging back and forth, things kind of wagged in a when you were moving in one direction, they would go down, and then you move to the, well, no, I'm not going to say this right. We've covered this. I'll just say it that way. As we know from episode 1 and 2, stellar aberration involves a motion that's 90 degrees out of phase with the motion that you expect for stellar parallax. It was a reasonable. The magnitude of the wagging around was appropriate for what we knew about stellar distances, which is to say nothing. But it turns out that Bradley didn't discover parallax because it turns out the stars were too far away for his method to be able to detect. He didn't have the sensitivity to detect that. His method could have found the distance to stars if they were less than something like 10 trillion miles away, but they aren't. They're further than that. So he didn't discover parallax. But he did discover aberration, and we've talked a lot about that in terms of the apparent direction to a star, in terms of your motion with respect to the light from that star, or what that does in a couple of ways. So we talked about the corpuscular theory, which leans primarily on Galilean relativity. No preferred reference frames. Starlight simply comes straight to each observer directly from the place of emission. So in Newtonian, aka Galilean relativity, there are no preferred reference frames. Every observer has the perfect right to think of themselves at rest, and light in that model simply comes directly to you from the place that that light was emitted. That's all you need to know about it. And that all worked pretty well. Bradley was able to explain aberration in terms of that, in terms of the fact that when 6 months at one point and then 6 months later, we are moving differently. We are in different reference frames, and therefore we see the source of the light in different positions, which gives us a different angle to that star. It makes the star look like it's in a different place in the sky. Okay, so finally on this slide, in 1819, and really, boy, within a year or two of that date, the corpuscular model of light bit the dust big time with the success of Fresnel's wave theory, an elaboration of Huygens from a century and a half earlier. And the success of that was especially strong because it predicted an incredibly counterintuitive and previously never seen thing, this Poisson-Arago spot that we talked about last time, and that I don't think I will review here. You can go back to the previous episode if you want to. The fact that that this was such a counterintuitive prediction, had never been seen before, was pointed to by Poisson, an enthusiast of the corpuscular theory, and he thought he had a gotcha. He said, your theory says there should be this spot. Ha! And then Arago went out and showed that the spot actually is there. And that was a seminal moment for the wave theory. Pretty much instantly made it bite the dust, although there's always hangers-on. So within 10 years, the wave theory was firmly established. The wave theory requires, or at least apparently requires, a medium, the so-called luminiferous ether, and an abandonment, at least in some sense, of Galilean relativity. There is now a preferred reference frame, at least for light, and there are now privileged observers, those who are at rest with respect to that medium, with respect to the ether. And there's a way to determine your own absolute velocity through the ether relative to those observers who are at rest with respect to the ether. Starlight appears to deviate from its true path through the ether due to each observer's absolute motion through that ether. So it's a very different view of aberration, even though it gives exactly the same result. There's no way of distinguishing between corpuscular and wave theory views on that basis. Okay, sorry, I talked on that one longer than I intended to, but this is a relatively short slideshow this time, so we will hopefully make up for that. But let me stop there for a moment and welcome Andy to the stage. Andy, hero protagonist. Nice to see you, Andy. And if anybody has anything to say now, or questions or comments, speak now or hold your peace until the end of the next slide. All right. Well, let's move
Hello.
right on. Oh, go ahead.
Just want to say good morning.
Oh, good. Yeah, nice to see you, Andy. It's always good to see you. Okay, let's move on to slide 3. So just a quick review of the corpuscular theory, what's going on and how to understand other observers' experiences. So in the corpuscular view, as I mentioned, light travels directly from where it was emitted in your current rest frame to you in your current rest frame. There's a little diagram there showing there's a source. That's where the source was when the light particles that you are now seeing, so there's the source of those light particles which are now entering your eye, and there's you, and nothing in there is moving other than the light particles. The light particles are coming from that source. Now that source may no longer be there at this point, but that's where it was in your current reference frame, as if you had never moved at all. That's where it was, and the light just comes straight into your eye. And nothing could be simpler. So then the only question is, how do you understand any other observer's experience, especially given stellar aberration, that other people will say that that light is coming from a different direction? You know, maybe not another source, but at least it's coming from a different direction. How do you understand? Somebody right next to you says, no, that's not the direction it's coming from. It's coming from this direction. And you say, well, wait a minute, that doesn't make any sense at all. The way you do understand it is simply to add the velocity of you with respect to the other person, which is a funny way of saying it because we usually think of the velocity of the other person with respect to you. And that's why I indicate there that the velocity of you with respect to the other is just the opposite of the velocity of the other with respect to you. As I've indicated in the diagram below, there's a little blue arrow, the velocity of the other with respect to you, and then you'll see in the frame to the right of that it shows up again in the opposite direction, the velocity of you with respect to the other. You add that velocity to the velocity of the light with respect to you, and you end up with the velocity of the light with respect to the other. And it's written out in terms there below. And I wanted to write it out like that just to make sure. You might say, well, how do you keep track of all that? This is what I always pointed out to students, and I think it's really a good way to think about this. Notice that the first term there, the velocity of the light with respect to you, and then I add the velocity of you with respect to the other. The fact that in that equation, the u is at the end of the first, the velocity of light with respect to you, and then it's the velocity of you with respect to the other, the u's cancel out because they're right next to each other, and you end up with the velocity of the light with respect to the other. It's only by arranging it in that order that you get the velocity of the first thing with respect to the last thing, by making sure that you are putting them in that order. And I won't spend more time on that unless somebody has a question. But that's a really nice thing when you talk about relative velocities, to be very clear about what it is that's moving, or what it is that has the velocity, and what it's with respect to. And if you always organize things that way, then you know how to add things to get the thing you want simply by arranging the two things in the proper order. Okay, enough said about that. Any comments, questions? And so anyway, so the result of that is that I can see what I see, and I can predict what any other observer will see themselves simply by going through that little mathematical operation. And then I can say, and I totally understand that, they're going to see the source in a different place, and they're going to see the light coming from that source in a different direction. So moving on to slide 4, what about the wave view? So in the wave view, it's a little different. Now light travels at the speed of light, because now there's a medium. That's the nice thing about the wave view, is it gives a reason for light to have a speed. And it travels perpendicular to these wave fronts that we talked about, in which you're certainly familiar if you've ever been to the ocean and seen wave fronts coming in and noticing that they move in a direction perpendicular, basically, to those wave fronts. It travels at the speed of light, perpendicular to the wave fronts, in the ether, in the absolute rest frame. Now there's this preferred rest frame. And I'm showing that there, over there, with the wave fronts and the rays of light perpendicular to the wave fronts. But I'm also showing what some other, what you or any observer actually ends up seeing. How do I understand my experience or any observer's experience now? I simply add the velocity of the ether with respect to you to the velocity of the light with respect to the ether. I should have written those in the other order, I realize now. But just like before, I've got that ether with respect to you, which is a weird way of saying it because we would usually think, what's the velocity of you with respect to the ether? That's just the opposite, as I'm showing below. And I've written it down there once again in the proper order. Take the velocity of the light with respect to the ether, add the velocity of the ether with respect to you, and you end up with the velocity of the light with respect to you. The ether cancels out because of its position in those two things, and you end up with the velocity of the light with respect to you. And so that's what you do, and you get the velocity of the light with respect to you as it shows there. And you would do that now for any observer, right? Notice that an observer that's at rest with respect to the ether is just going to see the velocity of light with respect to the ether. There's no velocity to add. But for any other observer, we just go through this process. And so we think of it now really in that way, in terms of the direction of these rays of light, rather than the direction, rather than where the light source was, even though we can do that as well, as I've said before. Okay, done with review, and halfway through the presentation in some sense. Any comments, questions? All right, so let's get into the heart of it. This is really the fun one because today we're going to go through the 1800s, and this is where the real fun happened. We went from corpuscular to wave theory. We had a series of really interesting, quote, failures that, well, we'll just talk about them as we get to it. And I think that I want to start the story with Arago. That's his name. That's how you pronounce that. I've just learned that today. Arago. Not surprising, I suppose. What he did, he was a corpuscularist, or at least he was, I shouldn't say he was a corpuscularist, but the corpuscular theory was reigning at that point. And in 1810, he did an experiment looking for differences in the refracted light from stars owing to their different speeds. Newton had a really interesting theory of refraction that involved light speeding up when it entered a medium. This is something I didn't know until recently, but he had a very well thought out theory of refraction that involved objects, light particles being attracted to matter and moving faster perpendicular to the surface when it was inside the medium than it did outside the medium. So that's something you can read about in the link that I put down at the bottom there, which is a wonderful link. Let me just say, rather than listen to any of the stuff that I've been talking about, you should just read that link and other things, because this guy has gone down the same path that I'm taking you down, and he's doing it with beautiful clarity online. So I just really strongly recommend that link if any of this is of interest to you. So he looked for these deviations because in the corpuscular theory, if the Earth was moving toward a star or a star was moving toward the Earth or away from, there would be differences in the speed of these particles, and those differences would show up in different amounts of refraction. he took a telescope, took the light coming out of the telescope, ran it through a prism, and looked for differences in how much the starlight was refracted, owing to those speed differences of the particles. And he found no measurable deviations. That was surprising to him, right? He expected to find deviations. That remains true to these days. To this day, there are no deviations when you send starlight through a prism or anything else. I mean, there's deviations due to the prism, but the amount of deviation doesn't change star to star. It doesn't change from June to December when the Earth's motion changes by 60 kilometers per second. So there's no changes there. It's as if the Earth were standing still. Certainly something you would point to if you were committed to that point of view. So there were no measurable deviations from that. And so 10 years later, when Fresnel solidly established the wave theory, with Arago's help, remember, because Arago actually was the guy who showed that the Poisson spot actually does exist. In 1818, Arago asked Fresnel if he could explain Arago's failure to observe any difference with the wave theory and the introduction of the ether. And that's the subject of the next slide. So once again, I'll just tout that article and the article from the same guy that appears on the next page. These are two really wonderful articles. I just couldn't recommend them more highly. Let's just continue with the Fresnel thing, and then I'll stop again for comments or questions. So he asked Fresnel if he could explain it. So what does Fresnel do? Fresnel found that he could account for Arago's result by hypothesizing that the ether exerted a partial drag on light, or maybe I should say the medium exerted a partial drag on the ether, I probably should have said, traveling through a medium. So when a medium moves through the ether, Fresnel said, well, what if the moving medium drags the ether with it? Not totally, but a little bit, depending on the index of refraction of the medium. So he said, so he hypothesized that the velocity of light in the medium, in the ether frame, was different from the velocity of light that it would have been if it weren't moving through the ether through this formula. You get the velocity C prime, the velocity of light in the medium, in the ether frame, is the velocity of light divided by the index of refraction, the unperturbed velocity of light divided by the index of refraction of the medium, plus a fraction, a weird fraction of the velocity of the medium itself. And he said, let's let that fraction be 1 minus 1 over n squared. Now, how did he come up with this? He came up with this purely because he wanted to show what mathematical relationship would explain Arago not seeing any deviation in the wave theory. So he said, if this is the case, we can explain Arago's result. This was not based on any theoretical model. There was no theory to back it up. It was a purely empirical, oh, yeah, that's a weird thing. How would we explain that? What if? And he put this thing out there, right? Most scientists should be very skeptical of something like this. Yes, it explains the result, but it seems like a special pleading. Why on earth would you expect this material to do anything other than a total drag? If it's going to drag the ether at all, why does it drag it in some fraction, some fractional effect? And why would it be such a weird 1 minus 1 over n squared? Where does that come from? Fresnel didn't know. He didn't have any place it came from. This is just what it would have to be if you wanted the wave theory to be consistent with Arago's result. That's really it. So very convenient, right? Let's stop there for a second. And I just mentioned that on this slide, I'm showing the difference between longitudinal drag and transverse drag. In Arago's case, he was looking for evidence of what would be a transverse drag, that the prism moving through the ether perpendicular to the motion of light should cause different deviations in the light. He wouldn't have seen it if it were longitudinal drag, because all longitudinal drag does is change the speed of the light. It doesn't change the direction, and he wasn't looking at the speed of light. He was simply looking at the direction. That's important for what comes later. There's another excellent resource down there. Let me stop once again and see if there are any comments in the chat, if any questions or comments from the stage. Oh, good. We have Jamal here. Okay, yeah, see, Jamal's not finding my presentation compelling. Well, that's not surprising to me. Anybody else? Any comments?
This ether drag, I'm not sure I really understood. So you're looking through the telescope, and there's errors that have to do with the lens of the telescope. There's errors that have to do with the atmosphere, and then there's the errors that have to do with stellar aberration. How would you in practice tell those apart? All you have is just a telescope and you're looking through it. And they're positing that, you know, if the ether is dragging partially, why not posit that it's the lens that is making something partially? I didn't get it.
Well, so presumably there'd be some kind of an effect, I suppose, from a lens to moving through the ether. Part of the problem with the lens is its kind of symmetrical shape. And so what Arago did was to put this prism on the output of the telescope. So you'd have the starlight. If you're focused right on this star, then the starlight's coming, you know, straight out the eyepiece in the back, and now you pass it through this prism. If that light happens to be traveling faster than normal, then the prism, the amount of bending produced by the prism should be less or more, you know, different anyway, than it would be, and under the corpuscular theory, should be different than it would be if, for instance, the light, let's say, if the particles are traveling faster or slower, depending on either the Earth's motion or the source's motion, then the amount of refraction in the prism should be different. So that's what he was looking for. There would certainly be effects of the eyepiece, but those would be kind of symmetrical. They wouldn't be expected to be off-axis bendings of the light. The atmosphere, of course, has its effects as well, but he was looking for how much the image of the star is bent away in the direction prisms always bend things due to that. Did that answer the question? I'm not sure I understood your question.
I'm not sure I understood my question. Yeah, I need to take another look at the beginning of the episode, because I was busy arranging the YouTube video. That's what happened.
Okay. Yeah, everybody's got an excuse, Shamash. I get it.
Yeah, I'm just dumb. That's the other excuse.
When I first met Shamash came into one of these things probably about 40 episodes ago or something like that. And he came in and slyly started asking some of the best questions I've heard anybody ask. And I thought, okay, this guy, he knows more than he's letting on. It's been really interesting having you here, Shamash, for that reason. A lot of people in here are of that ilk.
You're gonna make me swoon now.
And welcome, Benjamin. I don't know if you had a comment or question. You haven't unmuted, so I'll assume maybe not. But
well, I'm always going to be fascinated by the modern reintroduction of ether that comes from our quantum physicist friends.
Yeah, right.
In the chat, and you know, it bears at least a quick mention, doesn't it?
Well, we can talk about that in the after, and maybe we can talk about that when I do my next quantum-oriented thing. But unfortunately, we're gonna close the book here at about 1905, so won't be able to really say much, since quantum mechanics isn't even a thing yet at that point, and that won't happen until next week anyway. But yeah, no, those are all interesting things too, and I won't shy away from. We'll be happy to talk about them in the aftermath. Let's let's move on then. So Fresnel has this hypothesis, completely empirical. Just okay. Here's an experimental result. We think light's a wave. We think there's a medium. How do we explain it? He says, well, here's a way to explain it. No basis for this explanation other than the fact that it works in this one case. So that's where we are now in 1820, something like that. On to slide 7. In 1845, this is kind of a little known event, but it's kind of an important thing. George Stokes proposed a total ether drag theory that involved total drag in the medium and kind of a partial drag as light approached the medium. So the medium had an effect on the ether that extended beyond its physical location as it moved through the ether. Kind of a complicated theory, but a theory based on nothing other than trying to say, well, I think medium should grab the ether and then move it, and then there'd be some kind of effects off to the sides as well. And his theory explained Arago's result, and it was based on a model, unlike Fresnel's, which was just simply how to explain Arago's result, period. So in 1851, Fizeau conducted an experiment to test the different predictions of Fresnel and Stokes in this particular case. He sent light. He used an early interferometer that would be used of the type that would be used by Michelson and Morley later on. In the following arrangement, he had a pipe carrying water, as shown there in the blue, along that path, and then he took light from a source over there at the left, went through a beam splitter. That meant half of the light continued on through that beam splitter and half of it was reflected off the beam splitter, so that the light that went on, which was then reflected reflected once through I realize I described this experiment wrong up above. In fact, let me correct that now. I used the word twice because I had not even looked at my own diagram properly. Get rid of the word twice. I've just eliminated it if you refresh. At any rate, so the light comes through the beam splitter, passes against the water, and then reflects off of a mirror down to another beam splitter. We'll get back to that in a moment. The light that reflects off of the first beam splitter comes down and reflects off of a mirror and then travels with the water, joining with the other beam at the lower right beam splitter, at which point some of the blue beam reflects into the eye and some of the orange beam continues through, because that's what beam splitters do, so that they interfere at the eye, and there's a little picture of an interference pattern. We'll get back to that in a second. Go ahead.
Just a small question. The water pipe is not transparent, right? This is just passing next to the water, not inside the pipe.
No. It goes through the water. There's a transparent
through the water.
entry.
Okay, so there's some water going on, and the pipe is transparent so that the light goes through the water. Right.
That's right.
Okay.
And so you can imagine, suppose the light, suppose the water is traveling at some velocity, and suppose there's some drag. That drag will cause the blue beam to take a little longer than it otherwise would, because it's being slowed down by the longitudinal partial drag of the water that it's moving against. Whereas the red beam will take a little less time because it's being helped along by the tailwind of the water. And that means that when the light comes back together, you get this interference pattern. And one day I'll have to talk a little more specifically about interference patterns, but at least to first extent, we can just think either that light is in phase or out of phase. Turns out to be more complicated than that. But it'll interfere in some way at the eye, or there's probably a screen there. It's not really an eye. There's a screen there that the light is playing on, so that you can see whether it's interfering positively or I should say constructively or destructively. And now you change the velocity of the water. That makes the blue beam travel even a little slower and the red beam travel even a little faster. And that changes the interference. That's all we really have to say, is that it changes the interference. If you do a careful mathematical calculation, you can determine how much it changed. If the interference goes from constructive to destructive, then you've changed the interference by 180 degrees of phase, and that corresponds to a certain amount of extra time for the blue beam relative to the red beam, and that translates to a velocity in the water, etc. I've left all the math off here, but the math is not complicated, and Fizeau did this experiment and ruled out Stokes's theoretical model and validated Fresnel's empirical hypothesis. So it was rather remarkable that Fresnel's hypothesis actually won the day with Fizeau's experiment, because Stokes had a lot more going for it. Stokes had a reason for his theory. Fresnel still didn't have a reason, and to this day doesn't have. We now understand Fresnel's. I will next time point out that we now understand Fresnel's partial drag. That 1 minus 1 over n squared turns out to come right out of the theory of relativity. But he didn't know that. He thought it was an ether drag thing, and it won the day. As it should have, because it's correct, even though it's based on a complete misunderstanding of the physics. So I think that's one of the wonderful things here, is Fizeau was just trying to save appearances. He had no theoretical model. He was wrong about what was going on, and he got the right result, nevertheless. So that's kind of fun. Let me stop there for another moment.
I was today editing episode Philosophy Science number 7, and I remember we had a conversation about whether the truth of a theory can be determined by the accuracy of its predictions.
Yeah.
And I did not know about this example. This is a textbook, wonderful example of no, it can't.
Yeah.
The prediction
that's right.
here is absolutely right because it's based on empiria, but everything else is completely hocus pocus.
That's right. Yep.
So, question. I stopped my bike to say that.
Man!
I'm on a bike ride again.
When you stop Andy's bike, you know you've made a point.
I know. So my question was,
We should say happy clubhouse for Andy and happy more biking.
Well, I have a balloon. What is that? Does that mean it's my clubhouse birthday?
It does. Yeah.
Yeah.
Oh, I'm gonna stop and get some cake.
Excellent.
Okay, what was my question? My question was, okay, so if Fresnel's idea was correct, but without the theoretical underpinnings to be correct, would you be comfortable calling that kinematic equivalence?
I think it's akin. I actually, in some sense, I give kinematic equivalence more. I think I would probably give it more of a nod than I would give even Fresnel's. And partially that's because one thing I haven't said here is when I say Fresnel's theory was right, I really should have qualified that it's right to at what we call first order in V over C. So if you actually look at the relativistic result gives exactly the Fresnel's result to first order in the ratio of the velocity of the medium to the velocity of light. But it turns out that the relativistic result has terms to second and third, and well, at least second. I think to all orders. Now I have to think about that. But so Fresnel's result is not actually correct. It's just as correct as it could possibly be to the first order. That was all that was detectable in the mid-1800s. So yeah, I think I'd have to give the nod to kinematic equivalence because you can make a strong argument for that just on absolute terms. There's no fudging around it other than just the fact that it's unwieldy and doesn't have any cause. That's That's kind of the biggest problem with kinematic equivalence.
All right, how about this before I get back on? I heard the term recently, the undulating theory of light, and the claim was that that was in contrast to the corpuscular theory, and that the undulating theory of light was essentially ether theory, like it wave. Is that
Right.
I've never heard those two words connected like that. Is that true?
Yeah, well, that's the way I understand it. People used to refer to the undulatory theory of light, I think is what you're referring to. Yeah, and that's just kind of what it was called back in the day, as far as I understand.
Well, thanks. I will report back on the south side of the Golden Gate Bridge.
Oh, excellent. Man, you're crossing the Golden Gate. I want to be Andy. What am I doing here talking physics? Okay, well, we'll finish this up and I'll get my bike out. So on to slide 8, back to stellar aberration. We haven't talked about stellar aberration really specifically for a while. This is an interesting little thing that I was led to early on after the geocentrists and flat earthers. Geocentrists, I should say, and after the geocentrists, who I find kind of respectable at some level, and even the flat earthers point to Airy's failure all the time, which we'll get to here on the next slide. But a precursor to Airy's failure, as it's called, is a guy named William Klinkerfuse. And what Klinkerfuse did was to say, you know, that stellar aberration that Bradley saw was a result of the fact that the telescope kind of has to move. If you're moving through light, then as the telescope moves through the light's going to hit the side of the telescope unless you tilt it forward a little bit in the direction that you're moving, so that the light stays in the center of the telescope as the telescope moves. And then you're going to think you're seeing it in the direction the telescope is pointing. So that's what kind of that first, if you look at figure A there, it's kind of showing light coming straight down, but as it comes down, the telescope is moving to the right so that the light particles stay in the center of the telescope as the telescope moves.
This is due to the rotation of the Earth. Sorry, I'm interrupting, but why is the telescope moving again?
Right. So it would be moving for all sorts of reasons. The rotation of the Earth would be enough. Just motion of the Earth in general, if it's not the center of the universe. But in particular, and this is the most important thing, even if you think that at some point it's not moving, then 6 months later it has to be. Because we know that 6 months later, its velocity is 60 kilometers per second different than it is now, in a direction that we can also say. So we know that there will be differences in this direction that I'll have to point the telescope. And if we know the velocity of light, we know what those differences will be. They'll be 20 arc seconds, in fact, for stars that are directly above the ecliptic plane, because the speed of the Earth is 1/100,000th of the speed of light, and that turns out to translate to 20 arc seconds of change. And by the time of Newton, that part was understood. I mean, we understood. We didn't know exactly what the distance to the sun was, so we had maybe 10, 20, 30% slop in what the velocity of the Earth was, but we knew that it was on the order of 30 kilometers per second. And that's why Bradley was able to get such an accurate value for the amount of time it takes light to get to us from the sun. Was just based on we went through that last time. Sorry, I rambled there a little bit. Did I answer your question? Because I don't even remember what it was.
I just wanted to make sure. No, no, because
Okay.
in my mind, the telescope should not be moving on purpose. So a telescope that
Right.
wobbles around is not a telescope.
That's right. Yeah, no, we weren't moving the telescope relative to the Earth. It's just the Earth's motion. That's right. And so what Klinkerfuse did was he filled the telescope with water, which should make light travel slower, which means that you have to tilt it more so that the speed of the telescope itself, now the light's traveling more slowly. If you didn't tilt the telescope more, it would run into the back side of the telescope. So you have to tilt it more by that angle delta in the case of the water-filled telescope. But the weird thing about so he did this experiment. We'll just say he did the experiment, and because light travels more slowly, one might, I say naively there. You might wonder why I said naively, given everything I've said. Might expect the aberration angle to increase by a predictable amount. It's easy to predict how much it should change. It should increase by about 30%. Due to the telescope being water filled, and that's exactly what Klinker-Fuse found. That's what he reported that he found. So you might say, oh, well, cool. Except Fresnel's now validated but still empirical partial ether drag model says he should not have seen that additional aberration. If you apply Fresnel's partial ether drag model, remember that it was based on kind of why did Arago not see any extra deviation due to the prism, due to motion of the ether or anything else. Even remember a little more that it really says that you can't detect the ether at some level. That's really what Fresnel's empirical model was really kind of a way of explaining why we can't detect it. Klinker-Fuse was detecting it, and Fresnel said, no, you can't detect it. So there was a real conflict here between Klinker-Fuse result and Fresnel's model. So this raised a question in the mind of George Bedell Airy, slide 9. In 1871, 3 years later, Bedell redid the Klinker-Fuse experiment, and I've read Airy's paper. It's pretty short, and he talks about Klinker-Fuse having done the experiment, and he says very kindly, he says, because I can't remember how I should have had the actual text here, but because it hadn't been reproduced, he just thought maybe it was a good idea to reproduce it. I think it's pretty clear, this is just my opinion, that Airy looked at it and said, wait a minute, that can't be. Fresnel's theory says that it shouldn't happen, and we at least know that Fresnel's theory, as empirical as it is, does explain the Arago result, which is related very closely to this in terms of dragging ether drag. And if you incorporate ether drag, you certainly don't get the theoretical result that Klinker-Fuse expected to get, which he claims to have gotten experimentally. So Airy said, yeah, I'm going to redo this, right? So he redid it, and he found no detectable additional aberration. Now, it's interesting to note that his experiment is referred to as Airy's failure. And for the longest time, I thought myself that was a result of the fact that at the time, there was no way of understanding his null result, the fact that he found no detectable additional aberration. But I was wrong about that. One of the things I've learned in the process of putting this together is that by the time of Airy, Fresnel would have predicted the result that Airy got, and I think Airy knew that. Airy knew that what Klinker-Fuse had gotten didn't make sense, which is why he redid it. And so his failure was really just him getting almost surely what he expected to get. And what we now know is, I mean, it's not like this experiment hasn't been done better in the last 150 years. All of these experiments are now done to orders and orders and orders of magnitude better accuracy. So it is the case that there is no detectable additional aberration. That's not me kind of glossing over minor differences. There may be minor differences, but we still haven't seen them, and we're now capable of detecting them probably to 10,000 to 100,000 times greater accuracy. So that's what we say about Airy's failure. So it's called Airy's failure, even though that result is now fully corroborated and, as we'll see next time, trivially accounted for by the special theory of relativity. And it's also, I think, particularly fascinating to note that Ares' failure is a mainstay of biblically inspired geocentrists, not to mention flat earthers who are geocentrists kind of as a side note, as proof that the earth does not move, does not revolve around the sun, which I think is particularly priceless given the fact that the aberration itself, the thing that this additional aberration was supposed to be, we're supposed to be seeing additional aberration due to filling the telescope with water. Just the fact of aberration, the phenomenon itself, remains one of the strongest refutations of geocentrism, because you really can't explain it except for an Earth revolving around the sun, unless you want to go to the kinematic equivalence and then pretend that it's a dynamic equivalence that Andy was pointing to. The idea that, no, it's not the Earth revolving around the sun. It's the entire universe and every star in it revolving around the Earth once a year, right? For some reason, once a year. And then for no reason, right? Doing that for no reason, and doing it in a way that produces exactly the result that you get by simply letting the Earth revolve around the sun. Right? You have your choice of letting the Earth revolve around the sun for perfectly understood reasons, or letting the entire universe revolve around the Earth in a very slight, weird way once a year for no reason whatsoever. That's kind of your choice. All right, so I'm actually done with the presentation here. I'm just gonna look forward, and then I'll stop, and then we can talk about anything in the slides or anything else you want to talk about. Looking forward to next time. So as of 1871, all seems quite well. I mean, it's really important to kind of stop here and recognize that as of this time, with Ares' failure kind of putting the cherry on the pie. His failure actually kind of sealed everything up, put a nice bow on the package. Everything was well. We had the ether-based wave theory of light. Although the ether had not been detected, virtually no physicist doubted its existence. It had to be there because waves need medium. And there were no known experimental phenomena that were particularly troubling, as long as you were willing to admit this completely empirical result of Fresnel. Probably one of the outstanding questions was, why is Fresnel's partial drag what it is? That was probably the biggest question mark over physics at that time. But over the next couple of decades, innovation and especially the experimental genius of Albert Michelson produced this instrument, the Michelson interferometer, that would necessarily detect the motion of the Earth through the ether. It was easily sensitive enough to detect the motion of the Earth, because we knew already that motion changes by 60 kilometers per second every year, and his instrument would detect that. This has a modern parallel in LIGO, the Laser Interferometric Gravitational Wave Observatory. When they were building LIGO, the nice thing about it was that every physicist knew that this thing would detect gravitational waves. If it did not detect gravitational waves, then they didn't exist. In the same sense of Michelson, we knew the magnitude of gravitational waves predicted by the theory of relativity, the general theory, and we knew that there were sources that would produce those gravitational waves, and we knew that LIGO would detect them because it was sensitive enough to. So it had to detect gravitational waves, and had it not, that would have been a monumental event on a par with Michelson and Morley failing to observe the motion of the Earth through the ether. That was a monumental event too. And I want to be really clear that if it weren't for the fact that we already at that point knew for sure that the Earth was moving around the sun, the Michelson-Morley result would have shaken our faith in that result. So nobody was proposing that. We'll talk about that all next time. So, yeah, and then we'll get to the theory of relativity. We'll put a bow on all of this, and we'll move on to the next topic. So thanks, everybody, for coming. I'm finished. Come on up on stage if you want to talk or have comments or questions on slides or anything else, and I'm done.
Thank you, John. Wonderful as always. Waiting for part 5. Will it be the last part, or will you do like a 2-part series now?
Yeah, no, this will be the last part. Unless maybe I shouldn't say that quite so adamantly. I'm quite sure that we will do everything that needs to be done, because I'm not going to go into terrible depth in terms of the. I do want to talk a little more specifically about the Michelson math than I did about, for instance, the Fizeau math, which is similar. Fizeau also used interferometry. But ultimately, we're just going to talk about the Michelson-Morley experiment and then relativity. And then what I want to end with, maybe this is the most important thing to say, what I want to end with is the really neat way in which the relativistic view of what's going on here combines the best features of both the particle theory and the wave theory. And you might say, ooh, wait a minute, where have I heard particle and wave models of light before? You can make of that what you will, but it's really interesting that in relativity, you can use the velocity addition formula of relativity to derive Fresnel's empirical formula. So you show where it comes from relativity. So you can think of light in that way, but you can also think of it in the particle way, in the fact that relativity doesn't say that the Earth is moving now or 6 months from now. It's just that the Earth is in a different reference frame 6 months from now than it is now. And in that different reference frame, the source of the light is in a different position. The difference is that in relativity, the source of the light is in a different position that you can only understand, being another observer, if you understand the way space and time transform in relativity. In the corpuscle theory of Newton, you could understand another person's view of the source simply by saying, oh yeah, no, I get it. The person was over there. He was looking at the source when it was at a different time. It's the same source. He just has a different coordinate system. You think about it in particularly intuitive terms. In relativity, you have to do your transformation from one reference frame to another in a much more complicated, not much more complicated, but certainly a counterintuitive way than using the Lorentz transformations. So Hansen, surely I must have said something. I see Hansen down there in the bottom. I just always, Hansen has a pretty clear view of the theoretical aspects, more than I do usually. Certainly welcome, both you and Eric, Io. If you have anything to say, I'd certainly be pleased to hear it. Tear me apart. Let me just recommend one more time. If any of this is of interest to you, I really so strongly recommend those links on slides 5 and 6. I'm going to be digging into this guy. This guy's written a lot of stuff. He's a very clear expositor. I should have just not done this series at all and just had one series saying, go look at these things. They're really good. Oh, hi, Jesse. Welcome to the stage. Did you have something you wanted to say?
Yeah, I mentioned Lorentz transformations right before you did, and I was just so happy that I was like, yeah, it's like GR is so complicated because I tried going through Sean Carroll's book a while ago, and like it's it's a little terse. Those GR books, they're a little heavy-handed.
Yeah, GR is really a different thing. I mean, fortunately, we won't have to talk about that at all to put a bow on this series. We just need special relativity. And when I'm teaching special relativity, I actually kind of stay away from the Lorentz transformations. I think it's we had a previous series in the Bitophysics series. I don't remember where it is, but if you go to the if you go to the list of all of them, you'll find it where we talked about relativity from the point of view of nothing more than the relativity of simultaneity, length contraction, and time dilation. You can do basically all of special relativity, never even laying eyes on the Lorentz transformations. You can just think about things that way. And I find it a much more pedagogically attractive way to think about special relativity. But yeah, GR is another kettle of fish entirely, and I would be hard pressed ever. When I talk about general relativity, I generally like to talk about the understanding of the gravitational force without talking about curved space-time, even just talking about the fact that in general relativity, gravitational force, the way we understand it, is not existent. It's an inertial force like centrifugal and Coriolis forces, and that the only real effect of gravity are tidal forces, the way things change over spatial separations, not the effect on a particle.
Yeah. So one thing I brought up, I'm not sure if you're going to touch on it, is like debating about whether or not we assume space-time is emergent, like we take it for granted in the modern physics lens, or it actually is emergent. I don't know if that's a settled debate, but I'm interested in what your thoughts are on that, or if it's relevant.
Yeah, I think those go a little bit beyond certainly the types of things I like to talk about in this room. But I will say this about it. I mean, I think it really is important to understand. One of the things I've come to understand in the course of presenting this series, I think, and talking to people on Clubhouse, is how important it is to distinguish between the contents of a model and what goes on in nature. For instance, I can prove things in Newtonian mechanics. I can take the basics of Newtonian mechanics, and I can prove that the Earth moves around the sun in an exact ellipse, absent every other thing in the universe, right? Get rid of everything in the universe except the Earth and the sun, make the Earth and the sun symmetrically distributed masses, and I can prove that they orbit each other on perfect elliptical paths. But that's not a proof. That's not a proof about nature, and it's not. And it uses the ingredients of space and time as elements of the model. Ultimately, I can't even really prove that there is space and time other than I can't. I mean, that's an element of my model. What my model does is it predicts what some instrument will read if I deploy it after setting things up in some other way. I like to think of physical theory as doing nothing more than predicting where a needle on some meter will point. And then you can interpret the meaning of that number that the needle points to any way you want. Doesn't matter. If I was able to predict where that needle points, then I've done my job I've told you what nature will do. And that's all we can do, really. Everything else is interpretation. So in some sense, space and time is emergent in the sense that it's only part of our model. But that's not what you're talking about when you talk about emergent, and when other people talk about it, they're really talking about it really being an emergent property in nature. And I think that's just a dangerous path to go down. I don't even know what it means, because I don't think we can say anything about what's really happening in nature. We can only, we can say what happens. We just can't say why or what it means. Okay, well maybe we're moving towards a quick end here. I have to get on a couple things, so that works for me as well. Do
Maybe
come, yeah.
maybe
Go
I
ahead.
can say a few words.
Yeah, I'll do that.
On Wednesday we promised to create the scientific Discord server, and I finally managed to create it. Now it's still very rudimentary, like there's not a lot of stuff there, but this will
Oh,
be like our way to connect with each other, to send papers. We're all just a bunch of nerds, and we all are working on several different things, and we're all interested in each other's opinions. So if you just click on the link in the chat, this link will stay active forever, hopefully. And we will create some channels where you can post your work, you can post your dinner. It'll be a fun place. We will see where this experiment goes. But yeah, it's online now, so welcome everybody joining. I can see you.
excellent. I just joined.
I'll add you as an admin then.
Okay, cool. Let's see now what happened. Also, somewhere along the lines, I lost my clubhouse. There we are. Okay. Yeah, thanks for doing that, Shamash. I'm kind of semi new to Discord, and I don't understand my way around very
I'm
well.
completely new. This thing needs a PhD to operate, but
Yeah.
apparently it's good. So we will see.
Go ahead, Andy. Did you have something?
Oh, no, I
Oh,
just,
okay. It was a butt
I did, I,
unmute.
well, I did just sit down. So I haven't crossed the bridge yet. I decided to stop for for coffee and cake.
Oh, I say that. Which
These bike rides need to be properly fueled, and I like to take my time.
I thought maybe they had put a cafe at the midpoint or something.
No, still in Sausalito. I'm celebrating my birthday.
Yeah, right. Okay. Well, good. So once again, thanks everybody for coming. Do come to Shamash's thing on Wednesday, same time. Oh, and Sam's things on Monday, his chemistry things on Monday. I don't know if we've still figured out what time that is. Is it 11 or 12, Shamash? Do you
It's
know?
it's
Oh,
7
sorry.
GMT. It's
7
7 p.m. GMT.
GMT.
Whatever
So
it is your
that's
time.
11 Pacific, 2 Eastern, I guess. Yeah.
Yeah. 8 p.m. plus 1 time Europe.
Yeah. Good.
So he's doing thermodynamics. Next week in on Wednesday we will do Bayesian knowledge. Where's Benjamin? Is he still here? Yes, here he is. We're gonna do Bayesian probability and then some Bayesian philosophy as well. So yeah, if you're into that, show up Wednesday 17:30.
All right, really good. So we'll play ourselves out. What's it going to be? Maybe we'll. Oh, that seems like a semi-appropriate one. Maybe we'll go with this on the way out. Thanks for coming. See you next week.